So good evening, ladies and gentlemen. Physicists, and especially theoretical physicists, have a tendency of invading other fields of others, especially theoretical physicists. And like that, they're creating new fields which carry names, funny names such as econophysics or sociophysics. And well, this talk tonight is related to the field of neurophysics. And I'm actually in a program here, not the one you mentioned. There's a neurophysics program, neurophysics of space, time, and learning. And this today will have to do a lot with timing. Well, my subject is encrypted here, as you can see. It's, well, who can tell? Who can decode this? Well, you got it? Okay, I got it. I got rhythm. And so it's not only about rhythm, it's also about self-similarity. Because what you can see here, the second half is the same as the first half, just inverted. So played backwards. And so rhythm and self-similarity will be the topics. And rhythm has a lot to do with timing. And timing is one of the subjects of this research program here at the ongoing research program at the KITP. And actually tomorrow morning there will be a talk by Dean Buonomano. He's here perhaps, yeah, who will talk about various ideas and models how the neuronal networks of our brain can manage with this timing task for motor patterns and so on. Okay, but here our first aim was to understand what makes up a good rhythm, and can computers generate rhythms that are acceptable? So let me first show you an example of a master in rhythm. There's no doubt about it. So that's Ray Charles. And let's have a look at his performance in this Hit the Road Jack. Many of you will remember this. So let me play it. Okay, so when you analyze such a live recording and you analyze, say, the fluctuations, the rhythmic fluctuations, the temporal fluctuations, here shown in milliseconds, then you notice that Ray Charles slows down for some time. Here this is minus 0.4 BPM. This is not bytes per minute, not a new transmission rate. This is speed per minute. And then speeds up again, then keeps this speed for some time, and slows down, and so on. So this is a relatively rough analysis. We'll do better afterwards. Let's have a look at a more recent recording, so maybe 2 decades later, the Eagles' Heartache Tonight, and this looks much more regular. So there are several reasons for this. This kind of music, when it's recorded in a studio, they never play together. Right? One instrument plays after the other, and in order to synchronize these instruments, there is something that is called a click track, because in former times on magnetic tape you had different tracks, and so on one of these tracks there is a regular periodic click, like a metronome, and this helps to synchronize it and to keep the speed. This is not the only difference. Also, with the advent of digital editing techniques, it was possible to correct little errors. You can just shift the tones where you want. So, for instance, if I felt that this deviation of minus 50 milliseconds was too large, then I could shift it down to 0 where it should be. Well, but then if I correct all of these little deviations, then it might sound too regular. It might sound machine-like. Like a rhythm that is generated by a computer, if you wish. So then let's have a look at, or better listen to some computer-generated rhythm to get an idea. I'll play one. This is so-called, this is a Cuban rhythm, guaguanco. A little bit boring, right? So let's compare this with a human percussionist, and we've got Richard Hansen here tonight. Please welcome Richard Hansen. I was actually planning to have Monica Curry here tonight, whom many of you know. She's working in the housing office, and maybe perform together with Sarah Vaughan, who's also here. But she has another appointment, but she could help us send Richard Hansen here. And, well, you remember this, guaguanco, and Richard will now play. Okay. How about another one? Some kind of samba. Okay, thank you. So it sounds like alive and dead, right? So there is a difference. And you might ask, why is it possible to construct chess computers that are able to beat human chess players, and why is it not possible to construct a rhythm computer, a rhythm machine, that is able to beat a human drummer or a human percussionist? Well, there is actually a technique. So professional audio editing software offers a technique that's called humanizing technique, which simply adds random rhythmic deviations. Yeah, but the nature of such deviations in human musical rhythms had never been questioned. And this is what we have done. And so, as I mentioned, this is in a field that we call neurophysics now. One of the fields in which I've been working over the last 25 years. And, but it's more closely related to cognitive neuroscience and of course to musicology. But we are using techniques that are also used in so-called chaos theory or in statistical physics, time series analysis, and I'll come to that. Here's our experimental paradigm. We invited professional and semi-professional musicians to our lab. And for instance, here, Akbenyeba Atiok Beredlich, everybody calls him Pepper because it's such a complicated name. He was elected Best German Percussionist in a poll 2011. And we analyzed the rhythmic deviations in simple and complex rhythmic tasks. And then we asked the questions, are these deviations random? And are they correlated? I will explain what that is. And do they follow a law? And can we determine this law? Can you actually understand me, or do I need a microphone? In the back also? Okay. I'll show some experiments first, then explain the data analysis, statistical properties of these data, and give some applications, stochastic music and humanizing music, improving the humanizing techniques, and also talk about the perception of rhythms. Let me mention two of my main co-workers on this project. Holger Hennig was the credit student who was involved in that project, but was not his only project for his thesis. And Ragnar Fleischmann is a staff scientist in our institute. So here's the simplest task, which I used to explain what we're doing. So imagine we have a metronome. Here's the time axis. And the metronome produces beats at time M1, M2, and M3. And now a percussionist is asked to follow these metronome beats on a drum. And he or she plays sounds at times S1, S2, and S3. So they deviate from the metronome beats. And these deviations, we call them D1, D2, D3, and so on, Dn. So this gives us a series of deviations, D1, D2, D3, and so on, that we want to analyze. And this is something that we call a time series for obvious reasons. Here's such an example. The recorded sound from a drum. Green are the metronome beats, period 1/3 of a second. And red are the played beats by the drummer. And so there are these deviations that we have determined from the beat onset. Now in this way we recorded 1,000 deviations from 1,000 beats that are shown here in the example. So that shows the deviations in milliseconds. And this is just the beat index, so beat number 1, 2, up to beat number 1,000. And so that this shows the deviations of these beats. Now we want to ask how frequent are certain deviations. So, for instance, plus 40 milliseconds. Plus means the drummer played behind the beat. Negative deviations means he or she played before the beat. So how frequent are certain deviations? You see that large deviations of 40 milliseconds are very infrequent, occurring just once. Whereas 20 milliseconds occurs much more often. Now counting these deviations in bins, a so-called histogram, gives us such a distribution. So 40 milliseconds is very infrequent. So this shows the frequency here, only once. And many deviations occur around, well, here, 0, but not exactly 0. You see that, well, actually what you can see is that the average, or the most frequent deviation, is somewhat below 0. Negative values. So the mean, or the most frequent deviation, is about minus 16 milliseconds in this Gaussian distribution. That it's Gaussian is not so astonishing. And we also would like to know what is the width of this bell-shaped distribution. So what is the standard deviation from this mean? Oops. And that's also around 15 to 16 milliseconds for this particular drummer. Now this is really amazing. If you know that the fastest time scale in our neuronal networks is the time scale of an action potential, 1 millisecond. An action potential is action potentials are these pulses by which our neurons in our brain communicate, and these are 1 millisecond wide already, and so that a drummer is able to produce timing at an accuracy of about 15 milliseconds. That's really amazing, and shows how well performing our human brains are in this respect. Also opposed to other animals. Okay, now you might ask, is this typical that drummers play ahead of the beat? And well, the answer is no. It's not, and not all drummers play before the beat. But in our experiments, a majority had played before the beat, and a minority played after the beat, on average. Now I'd like to analyze more properties of this time series, and by applying something that is called stochastic theory. And I will try to make this easy to understand. But first, and so apply stochastic theory to such a time series. But first I have to tell you about tones and frequencies. So every tone has a frequency. So the frequency is the number of ups and downs in 1 second. So a low tone has a low frequency. Okay. And a high tone like 3 times higher frequency, has a high frequency. Okay. So 3 times as many ups and downs. That's the frequency of a tone. But here we are not dealing with tones. We are dealing with such random events, random signals. And there is this theory called stochastic theory, in which such one deals with such random signals. And they're also called noise. Why are they called noise? Well, let's understand this sequence as a signal and put this signal on a loudspeaker. And let's listen to this. So, obviously, such random signals that are not periodic can be understood as noise. And I will now explain a little bit this stochastic theory. There are different kinds of noises. There's, for instance, white noise, which has such a signal here. And let's listen to that. Okay, our signal had more low frequencies, as you could tell, than the white noise. There's also something that's called red noise. It has signals like this here, also random. They all are random, but they look different. Let's listen to red noise. Okay, it has even more low frequencies than our signal. Let me play our beat deviations again to you to hear the difference between red noise. It's somewhat in between white and red noise. Okay, so what you could hear is, red noise had more low frequencies. And this is something that we measure with the so-called power spectral density. You might call it also the frequency content if you add up frequencies, different frequencies, and analyze which frequencies are contained in such a signal. Then, this red noise signal has more low frequencies. You could hear this. Than the white noise. And this here is somewhat in between. So it's between red and white noise. Now this obviously comes from optics. Well, because in white light, all frequencies are equally contained. Red light has more low frequencies or long wavelength. And so this kind of signal is also called pink noise because it's somewhat in between white and red. And more exactly, if one does the analysis, then this kind of noise has a frequency content that rises at low frequencies like 1 over the frequency squared, so in an inverse power law. And this here rises like 1 over f to some exponent beta, which is close to 1. And so this doesn't rise as deeply as this rises at low frequencies. Okay. Now you understood what we mean by power spectral density. It's just the frequency content. And you actually can tell by looking at this, at these signals, that there are low frequencies. Right? Here the red noise, you see, has some kind of vibration here, So there are strong low frequencies in here. And not here. They all are equal. And here, well, there are a little bit of low frequencies, but not as strong as here. What we do as scientists when we have such power laws is we look at these power laws on a doubly logarithmic scale, and then these become straight lines, and from the slope of these straight lines we can read off the exponent. That was -2 here, f to the -2, and here it was the exponent beta, which is close to -1. So I will show you figures like this just to remind you, but this is purely technical, nothing very important. There is another quantity in stochastic theory I would like to introduce. That's the so-called correlation function. It's also some kind of memory. What is a correlation function? Well, it tells us how much a beat deviation at some later time is related to an event that occurred earlier, at some time t earlier. So it's co-related if it has a relation. So that's the correlation function. You can actually see this for red noise. If you have such low frequencies, strong low frequencies, then there are trends. So if the signal wants to goes up for some time, then it wants to continue going up. So there is a relation. There is a strong relation over a certain time. Some kind of memory. Oh my, running out of battery. Sorry. Always. Does anybody have a... This here? Okay, yeah. Okay, you can see this here, that there is a relation. Here you see there's nothing. Every event is independent from its predecessor. So there is no relation or an immediate decay of correlation. Every event is related to itself, but not to its successor or predecessor. So the correlation function goes to 0 from 1 to 0 immediately. Here, looking at this more exactly, we find that this correlation function, this memory, decays exponentially. And so there is a time tau, a time scale tau, over which this memory is correlated. But here, for this type of signal, we have an algebraic decay. Again, a power law, an inverse power law for the correlation function. And this gives a very slow decay. And these signals are correlated over many time scales, or we also say they are scale-free, because no scale is, there is no characteristic time scale.
Excuse me?
Yes?
The beat deviations are from an actual performance
Yes.
by a human.
Yeah.
I'm not sure where the red noise comes from.
Oh, this is generated by a random number generator that generates random noise of different properties.
Okay, so
Yeah.
that's completely random. The white noise is random too, but I don't understand why. I guess I don't know what white noise is.
Okay. White noise is characterized, can be characterized either by such a correlation function, that actually every event is independent from its predecessor. So there are random numbers that are entirely independent statistically from their predecessor. Okay, that's one way to define this. Another way if you define it like this, you find that the power spectral density, all frequencies are equally contributing. If you analyze the frequencies contained in such a signal, then all frequencies are equally strong. But this follows from such a definition, if you want. And red noise can be defined by random numbers that have such a correlation function, and then in turn we would get such a frequency content. And our beat deviations are somewhat in between. They have inverse power laws with an exponent close to 1 instead of close to 2. Okay, so I hope I made clear what this correlation function means, and that you can actually see it here in the signal. But what we want to understand are, of course, the beat deviations. And I already explained their correlation functions and their power spectrum, their frequency behavior. But now let's get to actual empirical data. When we do this with our beat deviations and determine the power spectral density, so this frequency analysis, that's shown here on a doubly logarithmic scale. So frequency is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. So 1/10, 1/100, 1,000. And this is shown here 10,000 and 1 million. So on a logarithmic plot. Then you see here, this is follows some straight lines. This is shown for different tasks, for hand beating on a drum and synchronizing voice with a metronome. And in all these cases, we find these inverse power laws where the power spectral density follows such an f to the minus something behavior. We have more accurate results that I'll show immediately, but just for completeness, I'm showing these power spectral densities. Well, I already said, I guess I can skip this, that this is something that's called 1 over f noise or 1 over f beta noise, depending on the exponent. And if we have if we find such a behavior for the power spectral density, then we can also determine the correlation functions, which also decay in an inverse power law. And we can determine the exponent gamma of this correlation function from the exponent beta of the power spectral density, as shown here. We have applied also some other techniques, so-called detrended fluctuation analysis. This is techniques of time series analysis. I don't have to explain how it works. Let me just say it measures, again, here our signal of beat deviations. It measures the strength of fluctuations over a certain time window of a certain length t. And this fluctuation function is shown here as a function of the size of the time window. And as you can see, we find, again, log here, we find very clean power laws, positive power laws, with different exponents. Now, it can be shown that all these exponents and all these power laws are related. If we measure such a power law t to some power alpha in the detrended fluctuation analysis, then we can show that the power spectral density also follows a power law with an exponent that is determined by the alpha in this way. So we can calculate the beta, and also we can calculate the exponent of the correlation function power law. So everything is determined by the alpha, Yeah. In order not to confuse you too much, I will now present everything in terms of this exponent beta of the power spectral density. So that's what we call 1 over f beta noise. And these are now our results for complex drum sequences, for synchronizing voice with a metronome, and for a simple tapping task, tapping with one's hand on a drum. And here you can see the different exponents beta. Those are the exponents of the power spectral density. And as you can see, they are different. They are close to 1, so close to 1 over f noise. Some are smaller. And they're not universal. In physics, one always tries to find universal exponents. Here, they're not universal. The fact that there are these power laws is universal. So all people who were able to play these rhythms from the beginning to the end showed such power laws. So they showed 1 over f noise, but the exponents were different. Yes? Different musicians. But here's a case of the same musician playing at 2 different tempos and had 2 different exponents. So that's not universal. Okay. But the conclusion is these power spectral densities follow such a form, 1 over the frequency to some exponent near 1, like 1 over f. And this implies that we have slow decay of correlations or long memory for these deviations. So after a deviation that is played after a long time is still dependent on a deviation that's played in the beginning. And we have self-similarity on many time scales. Now, this gives us an answer. What are the laws that human drummers follow when they play rhythms? And I told you about this humanizing technique, which is based on entirely uncorrelated random numbers, white noise. And we therefore proposed a new humanizing technique, 1 over f humanizing, and we got a US and EU patent for that. And I'd like to show you, to give you an example how this sounds. Our idea is not to humanize Bach's inventions, but these inventions by Johann Sebastian Bach, they have 2 parts, and so it's relatively easy to hear the differences, which you would not if I played a pop song to you. So that's for the purpose of hearing these differences more easily. This is invention number 1 with a relatively little standard deviation of 8 milliseconds, so maybe you wouldn't hear the difference. Let me play it to you. Okay. I would ask you which one you preferred. Okay. Who preferred version 1, version A? Who preferred version B? Oh, that's a majority. So, version A was on the F now is humanized. Version B. Okay. I noticed differences between people who have a musical training because you're used to you train yourself to precise timing. Let me give you an example with a higher standard deviation. Okay, this one. Okay, who preferred A? And B? Majority. Well, again, well, well, we had a. Okay, I can try another trial. The well-tempered clavier. Okay. Okay. Now, who preferred A? That's a minority. And B, I guess the majority. And, okay, now this time. Okay, well, this often depends on one's constitution. I don't know. Sometimes I hear it, sometimes I don't hear it when I have this, this small standard deviation. Mm-hmm.
When you play a Bach piece, the player has a lot of liberty in slowing down and speeding up, and it's not wrong if they do that.
Yes, sure.
It's a very different task.
Yeah, yeah.
It causes pressure.
Yes, of course. Yeah, yeah. Yeah, okay, okay, but there was no human player. This was computer generated. It was a MIDI file. So it was an exact file that we humanized.
Theo, were these standard deviations chosen for a good reason? Because before you were showing standard deviations that were
That's about the size that we have. And here you hear the difference much more easily. I'll show you an example where you won't hear it. Okay, real recordings. What we did is we got a local recording studio that created a song for us, recorded it, and humanized it. The song is Every Day, Every Night. And the singer was not humanized, only the rhythm section. And we played this to test persons. And let me play it to you. Well, and so on. You wouldn't hear a difference. But we had professional and semi-professional musicians of choirs in Göttingen listen to this with good earphones and so on, and they were not disturbed by anything. And then we asked them, well, I forget about this. We asked them, could you hear a difference? And 80% could hear a difference. And then we asked, do you have a preference? And 2/3 of the people had a preference for the 1/f version, as compared to the white noise humanizing, or, yeah. 39 test persons. Now, this song was not created to win the European Song Contest, in principle, but maybe it could even win the European Song Contest. And for those of you who want to take a note of, here are the lyrics. One day you came and made me see my chaos got no theory. But love, you can't explain, I didn't know what I would miss, but then you gave me your first kiss, I feel I go insane. Now, I thought this was something I should know. Well, but then I thought maybe I could compare this with Ray Charles. And it's actually not so different. War woman, oh woman, don't treat me so mean. You're the meanest old woman that I've ever seen. I guess if you said so, I'd have to pack my things and go. So it's compatible. Oh. Well, let me skip this because I want to show you something else in the end. This is a discussion in a forum of an online journal, Create Digital Music, where they discussed our work. And there are 3 different voices that, well, they are entirely going in opposite directions. But maybe I'll skip this. So we analyzed the statistical nature of temporal fluctuations in complex musical rhythms, and we found long-range correlations as a generic feature. That means long memories of these deviations. And the listeners preferred music with long-range correlated temporal deviations to uncorrelated humanized music. Uncorrelated means white noise. And, well, those of you who have access to Physics Today can find a relatively popular article in Physics Today, July 2012. I already mentioned Holger Hennig. But in the end, let me come to some related findings. Already in the 70s, Richard Voss and John Clark in Berkeley, where else, did an experiment. John Clark is an expert for Josephson junction and low temperature physics. And they had techniques to analyze fluctuations, noise in these Josephson junctions. And one day they thought, gee, why don't we put this on a radio station, and analyze radio stations, and they found 1/f noise. But not in rhythmic fluctuations as we did, but in pitch fluctuations, so in the melodies. And also on different time scales, on much longer time scales. And then they analyzed, for instance, the Brandenburg Concerto number 1. And they found this 1/f noise again, as you can see by the straight lines here. So this is for different radio stations, classical, jazz, and blues, and so on. They all have this 1/f behavior. Now you might ask, why does music in the melodies show 1/f noise, or these long correlations, slowly decaying correlations, without scale, self-similar correlations? Well, I give you an answer by playing music, some kind of music that we created by using 3 stochastic time series, random time series, for the pitch, the rhythm, and the loudness. And we did this for diatonic, pentatonic, and chromatic scales. The most convincing is the pentatonic, for certain reasons, because we always interpret some kind of harmony, and so to exclude these effects, I use the pentatonic. Let me play this to you. So stochastic music with wide and uncorrelated time series. Okay. There is no correlation, right? Everything is independent in loudness, pitch, and rhythm and length of the notes. Let's do this with red noise. So very persistent, very boring. Both are boring, actually, after some time. So when it was high, it continued high. When it was loud, it continued loud, and so on. Now let's try the pink noise, the 1/f correlated sequence. So which one did you prefer? Well, I think it's evident. And, well, what's the reason for it? I guess it is, well, for the white noise, it's total surprise. There's no relation. The red noise is too predictable. And the pink noise is balanced somewhat in between surprise and predictability. So it is somewhat predictable, but also has changes, has some surprise. So it's balanced, and it's self-similar on many time scales. Again, one might ask, why? Why do we like to hear music that has this type of correlations? Slowly decaying correlations. I tried to give you an answer on this. It's somewhat speculative. We don't know so much about it. Oops. Well, one reason is composers remember their motives, and they take them up and vary them throughout the composition. If you listen at Beethoven's Symphony No. 5, it's full of these repetitions. So there is the opening motive that everybody knows, of course. Let me play it to you. Yeah. And when you listen carefully to this symphony, you find this reoccurring all over the composition. For instance, in the third movement, it comes up in this following form, in not 2 quarters, but 3 quarters, and somewhat faster. So that's one of the reasons for this type of self-similarity, that this is just reoccurring. There's also something called phrasing. That means that these little motives are put together, like here, what I just played. They are put together to form a larger phrase, and several larger phrases are put together to form even larger phrases, and so on. So this is also some kind of temporal self-similarity or some hierarchy in time.
How long are the phrases? I don't read music.
Okay.
I mean, can you tell me actually?
Yeah. These are the first 4 tones. Okay. And then it's repeated. Here, here, and then this. This changes slightly.
So I can give you another possible explanation.
Okay.
There's a time lag in our interpretation. We sense something.
Yes.
It's true for all the senses. For the ears, it's a quarter of a second approximately. So we can, if we hear something, and then something happens,
maybe
a quarter of a second later, we can still revise our interpretation of it.
Exactly what I was going to say.
Oh.
So you might ask, so composers do this, right? They use phrasing and so on. But why are they? You might ask, why are composers doing this? In cognitive science, there's something called chunking. Huh? And the reason for the chunking is that we need to store information. That's what you just said, right? We need to store information. Let me give you an example. Here's a sentence. It's almost German, that's why I used it. And in 2011, the new building of the Max Planck Institute for Dynamics and Self-Organization was completed. So in order to understand the sense of it, in 2011 was completed, you have to read the whole sentence. And you need to store the whole sentence. And this also happens on much smaller scales. Like, in order to understand the word self-organization, you have to store these 7 syllables, self-organization. Right? And then you get the sense. Then you get the word. And then there are smaller scales of phonemes where you also have to store. And this is the name of the institute. And we store on different time scales. We need to store when we listen to music, when we listen to speech, and so on. And there's a so-called ultra-short time memory, eco memory or so. That's phonemes and so on. The short time memory and so on. So it's known in cognitive science that we have such memories. They are investigated and so on. We don't know so well where these memories are, but we know their properties. And so we store on different time scales, and therefore we need to speak also with phrasing. There are some exceptions of people who speak without interruption, but usually we phrase. And I guess since our brain works like this, also the composers use phrasing, and not only for speech. Okay. That's it. And this is what I think is what's behind the self-similarity in music, why composers compose in a self-similar way. And in the end, now my hour is over, I'd like to play an example to you of extreme self-similarity in a musical composition. And that's from the Kunst der Fuge, the art of the fugue. And it's Contrapunctus 7. It says per augmentationem and diminutionem. So augmentation and diminution. This refers to the speed of the theme. First, let me play this. So it's 4 parts, 4 voices, and it starts in the third. So let me play the theme to you. Okay. Then after one measure comes the next, which is the first voice here. So you might have noticed it's upside down. This goes up and then down, and this goes down and then up. And it's also half the speed of what you heard before. Then in the third bar comes the second voice. That's not the right one. Sorry, this is... No. Stop it. Okay. Why? This should be the one. So it's again the speed of the original speed. Right? And now comes the last one down here after in the fifth measure. Okay. So this is a quarter of the speed of the first one. So you can hear this at 3 different speeds. And this comes all over the composition, which is here. So those of you who can read music, sheet music, this theme comes up all the time. For instance, here it comes in the third part, the slow one here. Or here, okay, in the second part, just before it starts in the third. So all over. And actually, if I hadn't played this to you, you wouldn't recognize. You actually will not hear this slow part. And this is also related to the way we process it, to our memories, I guess. This is just too slow. When you hear it, you don't realize that it's the same melody, just played slowly. Okay, so now I will play this to you in the end. And not myself, of course, or it's a recording. And while you hear it, you might think of what your brain is doing to listen to music. I mean, to store the music in its context. Right? Something we do automatically, and we usually don't think about this, that we are permanently storing new information in order to put it into a context. But that's what we are doing. And so let me play this to you, and it takes 5 minutes, I think. And So in the third, the second, no, it's in both of them. Thank you for your attention.
Questions? Let me just get the mic to you. Yeah, thanks. Have you ever considered analyzing distortions or deviations in musical instruments themselves? I mean, what comes to mind is a Stradivarius. Maybe the distortions give a very pleasant sound, similar to like in audiophiles, often for vacuum tube amplifiers to transistor. So.
Can you repeat the question? Or?
Yeah, the question was whether we have studied such distortions also in comparing different instruments by different violin makers, for instance. But we haven't done this. But of course, people are analyzing the sound characteristics of different instruments. Yeah, but would be too far from our field.
On a practical level, don't you require on some time scale for there to be negative or autocorrelation? Because otherwise, if you have clustering, let's say of a lagging beat, and that just and with a positive correlation, positive autocorrelation in the time series, then that means you're going to fall farther and farther behind. There needs to be an innovation or a shock, right, to bring you back to the beat. Otherwise, you're going to lose the time entirely.
Yeah. That's possible.
So I mean, in which case that would just be some sort of natural reversion to the mean, which you would expect to see in a natural system.
But then you would look at the absolute value of the autocorrelation function, and again this would decay. But that's possible, of course, that you have these anti-correlations.
So I guess I imagine if you showed this data to an evolutionary psychologist, they would try to make some argument about or correlation between the preference of humans and what they would naturally experience. So if you took a recording of a natural environment, would you experience the same power spectral densities of distributions of frequencies and rhythms?
Good question. Well, it's known that in natural images there are such correlations. I'm not sure whether this is the case in natural sounds, but it could be. Like natural noises, you can actually, if you're a tinnitus patient, like I had a tinnitus, I have a tinnitus, but when I started the new year, coming back from a skiing holiday, and looked at my schedule for the first week in the year, my tinnitus went up tremendously. And so I asked one of my colleagues in this Bernstein Center for Computational Neuroscience, who is in the medical clinic, and he told me, look up noises, bathtub noises, and so on in the internet. Because I said, when I hear the bathtub, it's fine. I don't hear my tinnitus. And so you can look up these noises, and apparently they claim this is one over F kind of noise. Right? What they propose for as natural noises, waterfalls or bathtubs and so on. Could be, yeah.
Have you done any experience where people have used drugs and done their music?
That you know about?
Well, no, we haven't done any experiments, but as far as I know, people like John Coltrane, Charlie Parker, and more recently Stan Getz, and I don't know how many have done the experiment, and I wouldn't like to repeat it.
Okay, on that note, I think we should, yeah.
Of course, there's this well-known book, Göttingen, Bach.
Yes.
So, any of these issues touched upon this to your knowledge?
Well, there is, of course, Doug Hofstadter writes about self-similarity a lot. But this kind of thing is not in his book, right? The rhythmic deviations or something.
Yeah, okay.
Great. Well, let's thank Theo and remind everybody there's... And we do have light refreshments, though they won't modify your rhythm near the courtyard.